Joe, can you hear me okay online? Let me get that. Testing.
Yes, I can hear you.
Perfect. Thank you.
Okay.
Here's a good one. Oh, you sure? Yeah, I'm just testing it. Joe just told me you can hear me. Testing. Testing. Good. Okay.
Yeah, if you notice anything. Everybody.
Sorry. Oh, yeah. Good.
Hello. Oh, there you go. Welcome to Astronomy. Would everyone please be sure to silence their cell phones? And our speaker will be introduced by Jane Wood.
Good afternoon, and welcome to our last class in astronomy. I am sorry it has to end, yet we close on a good note because our speaker today is Corin Marasco, who is a grad student at UF and in the Department of Astronomy. And when I first spoke with Corinne, I asked her what drew her to the stars, and she told me how when she was a child, very often her father would wake her up in the middle of the night, and off they would go to dark sky places where they would observe meteor showers, lunar eclipses, and whatever else graced the night sky. So that ultimately led her to Georgia Tech, where she majored in physics with a concentration on astrophysics. And during that time, for 2 summers, Corinne worked with NASA. And then on to grad school, where now Corinne researches stellar and galactic evolution. She focuses on asteroseismology, which studies not earthquakes, but starquakes. And as if that's not enough, in her spare time, Corinne runs her planetarium shows in public schools to get young people all excited about the field of astronomy. One other thing. Okay, so when I was talking with Corinne, I was imagining her on the weekend in dark sky places like she was with her dad. And she'd be out there, and of course, she would have her own telescope, maybe one of those big ones, the kind that it takes 2 people just to lift them out of the car. So I asked Corinne, what kind of scope do you use? And Corinne told me very humbly, she said, well, I only use telescopes that are in space. So Corinne uses telescopes that orbit the Earth. Please welcome Corin Marasco.
Wait, can you? Okay. Hello. Thank you so much for that nice introduction. That was very sweet. So hi, thank you guys all for coming, and I'm excited to be talking to you today. I haven't used a mic before, so if I get too far from it, could you let me know if I'm not speaking into it? Okay. Yeah, that might be better. Okay. Oh, that's better. All right. So yeah, today I'm going to be talking about giant stars, which is what I study, um, and telling you how we learn more stuff about them. So yeah, starting off, Jane already gave a really nice introduction, but just a repeat, I'm a 3rd-year graduate student at the University of Florida, and I love stars. That's why I study them, and I've always loved looking at the night sky and everything. I'm from Johns Creek, Georgia, which is just that circled part up there. And then for college, I went all the way to Atlanta. So yeah, really getting out there. But yeah, now I moved down here. So I'm at the University of Florida, first time living out of state. So it's exciting. And I also have a cat, and she's the cutest. Her name is Mavis, and she does a really great black hole impression. There it is. She curls up and sleeps like that. She's so cute. Okay. So today I'm going to be going over the scale of stars, and then a bit about like how we classify stars, something called the HR diagram, then stellar evolution, and then finally ending with what I'm working on, which is asteroseismology. Okay, so why do we even care about stars in the first place? So they're the building blocks of the universe, which is sort of what we call them. They not only make up galaxies, but they also host planetary systems. So they make up things as small as like hosts of planets to as large as galaxies. And yeah, so they're essential for both planetary and galactic astronomy. And they let us learn about the planets that orbit them, but they can also tell us about how and when galaxies were formed by just studying the stars in the galaxies themselves. So we should learn as much as we can about them. So just to give you an idea of just how big these stars are, I wanted to go over the scale of giant stars. So my analogy that I've got.
Pam's not there, Chrissy's there, and Chrissy's having as much trouble as Pam does.
Hello.
Chrissy hasn't done this before.
Am I doing something wrong? Okay. Oh. Okay, thanks. So my analogy is if the Earth was the size of a tennis ball, then how big would these stars be? So if the Earth was the size of a tennis ball, the moon would be about the size of this ping pong ball. And then does anyone want to guess on this scale how far away the Earth would be from the moon?
240,000 miles.
Oh, that's a good guess, but it's not quite that far. Okay, let me know if you need to do that. Sorry. Okay. Oh. Could the online viewers please mute their mics, if you don't mind?
Slides aren't showing.
Oh, okay. No, I'm sorry about the interruption. Yeah, keep thinking about your guesses in the meantime. We're good? Okay. So it would actually be a lot shorter than that. Oh no, now the thingy isn't working. Okay. It would be 7 feet. Well, it worked because he clicked it. Yeah, so it'd be 7 feet, which is larger than what I thought. I thought it would be like this big. But the distance between the Earth and the moon is actually so big that you could fit all of the planets in between it, which I didn't know. I thought that was cool. So if the Earth was the size of a tennis ball, on this scale, then the sun would be about the size of like a 2-lane road. Yeah, so a lot bigger than the Earth, but the sun is a relatively really small star. So looking at the bigger stars, they'd be about as tall as like the Freedom Tower. Yeah, so Sirius is the brightest star in the night sky. Even on this scale, it's not that big. Arcturus and Rigel are other stars in the night sky. And yeah, so Rigel is what's called a blue giant. They're very big. So as tall as the Freedom Tower on this scale, but they get bigger. So this is a red giant. It's what the sun will turn into in the future. So that's why it's called future sun on here. But yeah, so that would be about the size of a city on this scale. And then there are even bigger red giants. So this is one of the biggest red giants called Betelgeuse. It's in the constellation Orion. But yeah, so that would be about the size of LA, I think it said. So just a little bit larger. The largest star that we know of technically is UY Scuti. Yeah, so they get very, very big is basically my point here. Yeah, and over 2 trillion suns could fit inside Betelgeuse, and the sun was already pretty big on this scale, so you can imagine it's very large. Okay, so now I'm going to talk a bit about how we classify stars. So the history of stellar classification is pretty interesting. At Harvard in like the late 19th, early 20th century, they employed women as computers, which would do, so they would do the grunt work for astronomy professors at Harvard, like looking through all of these glass plate slides. Yeah. And just writing down what was on them. And so through all of those studies, they noticed that they could sort the stars into different groups. So a woman named Wilhelmina Fleming classified them into groups of A through Q, but then Annie Jump Cannon came along and she made the system a lot simpler. And she created the OBH. You know what? I'm not gonna say it. Okay. She created that system. So here's a bit more about that. So this is how we categorize stars on a scale of OBAFGKM, and they start at red, which is M, and it's also the coolest stars. And then as the stars get bluer, they get hotter. So yeah, so blue stars are actually the hottest and red ones are the coolest, which is opposite what you would think. But if you imagine like a candle flame, the blue part is always like at the center. So that's where it's hottest. But yeah. Oh, and this is how we remember it. Oh, be a fine girl, kiss me. So that's a good way to remember the order of the stars. So with this system, it makes it really easy because we can tell like what increases with each letter. So as the star gets bluer, like I said, the temperature goes up, but also the luminosity. So blue stars are a lot brighter usually. They're also usually bigger, except for red giants. I'll talk about that later. But their lifespan is a lot shorter. So red stars live the longest because they don't burn through their fuel as quickly, because blue stars are just really like going at it. And so they run out of fuel a lot quicker than the red ones. But yeah. Okay, so the HR diagram is sort of how we depict all of these stars together. And it goes, so one axis is the luminosity of the stars. So it goes from faint stars to bright ones. And then this is the OB, a fine girl kiss me scale that I was talking about. So it starts at hot in the blue side and then goes to cool on the red. So these are a bunch of stars that are in the night sky. That's why they're labeled like that. But yeah, they go from blue to red, and then like diagonally, they go from small stars to big stars. So I'm gonna walk through each of those sections. So starting with what's called the main sequence, that's this sort of S-shaped curve right here. And 90% of stars lie on that main sequence. But what you see in the sky are a bunch of these giant stars because they're so big and bright. That's what we're able to see from Earth. So yeah, there are blue giants, which are just big blue stars, basically. There's red giants, which happen really late in a red star's life. They get really, really big and turn into red giants. And then some stars even become red supergiants. So those are, yeah, about like 10,000 times the size of the sun. So they're very big, but only some stars get that big. And then there are also dwarf stars, which are these little scattered ones down here. But I don't care about those. I care about the giants. But a lot of people do study them, so yeah. So just based on what I said, does anybody want to guess what type of star the sun is, which is this pink circle right here? Yeah, that's perfect. So the sun is a G main sequence star, or a yellow main sequence star. Yeah, so G and yellow kind of mean the same thing. Okay, so the HR diagram is really helpful for explaining stellar evolution. So that's why I was showing that first. This is what stellar evolution looks like. A lot of stars start on the main sequence. Like I said, most are main sequence stars. And then as they get older, they start to run out of fuel. All stars burn hydrogen at the beginning of their lives. But then as the core heats up from all of that hydrogen burning, it becomes hot enough to fuse helium. So then it becomes a helium burning star. So this is as it starts to run out of hydrogen. Oh wait, here I've got a, yeah. So as it starts to run out of hydrogen, it leaves the main sequence. And then eventually it goes through what we call a helium flash, which is when the helium all of a sudden ignites and starts burning. That's why it jumps up towards the hotter part. And then it starts helium fusion, and all of that like heat in the core makes the outer levels of the star expand. And then that's why they get so big and become red giants when they start to die. So, yeah. Now, the evolution of stars depends on mass. So stars like the sun will go through the process that I just explained, but bigger stars won't even have a helium flash. They'll just keep burning more and more elements. They go all the way up to iron. And then when they burn iron, iron can't fuse into any other element and create energy, basically. So, so they die when they start to fuse iron. They run out of fuel that way. Yeah, but for high mass stars, when they suddenly run out of stuff to burn and are just iron, they go supernova, which means, yeah, which means that, so the core stops burning, it becomes cold, and then all of the outer levels of the star, which were being held up by that nuclear fusion, gravity makes them all collapse in, and then they sort of bounce off the center and explode into this big supernova. So from that sort of last stage of their life, stars can turn into three kinds of things. White dwarfs, neutron stars, or black holes. So I'm going to go through each of those. So this is a white dwarf. This is what happens to the low mass stars. They're very, very hot, nearly 200,000 degrees Fahrenheit. And this is where the atoms are contracted as tightly as possible. So each atom is pressed up as close to the other atoms as it can get physically. And it's as massive as the sun, but only as big as Earth. So these things are very, very dense. It's powered by leftover heat from the star, so it's not actually fusing anything, but it still glows very, very brightly because it's so hot. Yeah, and then it slowly dims over time, eventually becoming what we think is a black dwarf, but we haven't actually observed any of those. Yeah, and then, so for low mass stars, what happens to the outer levels of the star is they sort of just fade away while the core becomes this white dwarf. But they look really pretty when they start to fade away. They turn into what we call planetary nebula. So these are pictures of planetary nebula. At the center, you can see the white dwarf, which used to be the core of the star. And then all of this used to be the outer layers of the star. So yeah, that makes pretty pictures. So the next thing is a neutron star. This is what happens to the higher mass stars. So all of that pressure from the outward levels collapsing into the core shoves basically electrons and protons together, which shouldn't be possible, but there's just so much pressure that that's what happens. So it makes the densest thing in the universe, well, the densest object in the universe, because black holes are a little weird. But yeah, so one sugar cube of a neutron star would equal the mass of the entire human race. So if white dwarfs were dense, these are like incredibly dense. Yeah, and so neutron stars rotate, but just like Earth, their magnetic axis is not aligned with the spin axis. And so, well, first of all, neutron stars are very, very powerful magnets because of their, just how much energy they're generating. They generate like, well, like, okay, did I put it? Yeah. So if an MRI machine is already really powerful and can like rip metal through a human, these are like 1 trillion times as powerful as that. So extremely, extremely powerful magnets. Of course. Thanks. Does anybody have, wait, does anybody have any questions in the meantime? Yeah. Oh, that's a really great question. I'm going to make you wait a little bit because I do get into that later. But hold on to that because that's what I study. So, do you have another one? Yeah. Yeah, so that's another really good question. So all of the iron at the center becomes like the neutron star, sort of. So when all of those elements get packed that closely together, they just all become neutrons because the electrons and protons fuse and become neutral. And so they don't really become an element because there's no room for the electron shell around the neutrons. So they're not really an element. They're just neutral. But yeah. Oh, that's a great question. No. Um, no, because they're smaller than elements. So the periodic table does not have electrons, protons, and neutrons, but it has everything else. Except quarks. Those are even smaller. But
Okay. Okay. That's why we did this.
okay. I'm gonna go back a little bit. If I can't move it. Okay, thank you so much. Okay, so like I was saying, the spin axis is not aligned with the magnetic axis. And the magnetic axis is so strong that it shoots out these jets. And because the spin axis isn't aligned with them, as the star spins, the jets kind of wobble like that. And so they periodically hit Earth, and we can see them as a bunch of X-rays. So we know that there are neutron stars out there because we get like an X-ray burst every once in a while as the star is rotating. And they can rotate really, really fast. So they look kind of funny like that. So the last thing you've probably heard of that big stars can turn into is a black hole. So this is the most dense thing in the universe that we know of. It creates a gravitational pull that is so strong that even light can't escape it. And so that's why it's black, because there's literally nothing there, which is kind of crazy. And its gravity is so strong that it bends space and time. It kind of like breaks the rules of physics. So that's why all of this light is sort of like distorting into a ring around the black hole. Yeah, things get really weird as you get close to a black hole, but it's very cool. So we call that limit where you can't see anything else, like this black part or this black part, the event horizon. And so that is the point at where light can't escape anymore. So that's why you don't see anything there. It's because no light can come out of it and into our eyes as photons. So we don't know, and we'll probably never know what is beyond the event horizon, which is crazy. That makes me upset because I want to know. But there is just no way to study it. So the only thing that we can do is guess, but that's for theoretical physicists. And that's too hard for me, so I don't do that. So these are both what we call stellar mass black holes, which are stars that have turned into black holes through the process that I was describing, the supernova explosion. They can be in pairs with other stars. So sometimes they're orbiting a star and will eat it. So that's what this is doing. It like pulls on the outer layers of the star and accretes them around this little black hole. And they're just alone in space. So they're kind of small. They're about the size of 10 suns. But yeah, they just float around. But then, oh, and we think some might have planets orbiting them, possibly, because some stars could go supernova, but still have existing planets around them. So I think in the movie Interstellar, if any of you have seen that, they go to planets around a black hole, and that could theoretically happen, which is cool. So then there are supermassive black holes, which we don't know how they form, but they are basically like ginormous black holes. If stellar mass ones are 10 times the size of the sun, these are millions, billions, and even trillions times as massive as the sun. So these are at the center of galaxies, which is what these pictures are. And they're so powerful that they make these giant jets that come out. This is the supermassive black hole at the center of our galaxy that we've taken some pictures of. You might have heard about like the first picture of a black hole. That was the black hole at the center of our galaxy, which is called Cygnus X1, I think. So it's not called that. I don't remember what it's called. I'm so sorry. Okay, so this is what I study. It's called asteroseismology, and Jane gave a great description of it. It's basically the same as seismology, which is studying earthquakes, but in space, so starquakes. So when a starquake happens, it sends these oscillations throughout the star, and these waves bounce around and make the star pulsate. So it gets a little bit brighter and dimmer and brighter and dimmer. And based on like the frequency of its brightness changing, we can tell what's on the inside of the star because the waves have to pass through that to end up making the star pulsate. It's also pretty new. It was first used on a big sample of stars just over 10 years ago. So we're still sort of calibrating it and getting used to using it and using it on larger and larger sets of stars. So because these waves travel throughout the inside of the star, they can tell us about the star's structure and composition. Sort of like when you play the same note on different instruments and it sounds different because they're made of different things. This is sort of the same thing. We call it like the sound of stars because these waves travel throughout the star and make it sing differently. And we can hear that song by just looking at the star. So, okay. And because the waves travel throughout the center of the star, they tell us about the star. And then like I was talking about earlier, with the OGBK, yeah, all of that, we know that bigger stars live much shorter lives. So if we know that a star is like blue or red or something like that, we know about how long it's lived for. So that's how we get ages using astroseismology. And that's what I'm working on, is getting the ages of stars. So yeah, and it's expected to be a lot more accurate than older methods of age determination. So it could be a really, really useful, like game-changing thing if we can get it to work, which is the hard part. Okay, so like I said, it's sort of like listening to the music of the stars. So this person turned light waves into sound waves. And I'm gonna play it, but it's very loud and annoying because stars aren't pretty. So just prepare yourself. So this is listening to what a star sounds like. Okay, I'm gonna cut it off there. But yeah, so it's really cool that we can do that. I think that's a lot of fun. So why do we even care about the masses and ages of stars? Like, why do we want to figure those out? Well, it helps us because we can determine when different galactic regions were formed. So like sometime, we don't know when yet, but sometime a bunch of different galaxies merged with the Milky Way and sort of imported a lot of new stars. and we don't know when those mergers happened. So getting the ages of stars could help us figure that out. And then we could also tell if a star is old enough for a planetary system to have like developed life. If we know how old the star is, we know how old the planet is. And then if the planet has been around for billions of years, we know that it's more likely to have life than a brand new planet. So that's how it helps planetary scientists and galactic scientists. Okay, so like who cares about my project specifically? My project is calculating the ages of stars from a telescope called TESS, which is that one. Like Jane said, it's in space, and it stares at stars for really long periods of time. And so we can get the frequency of those oscillations over time. But it's really difficult with TESS because it observes the whole sky in short bursts rather than staring at one point for years and years, like the other telescope we use, which is called Kepler. But Kepler's field of view is really small. It's only looking at a small portion of the sky, but TESS is looking at the entire sky. So we can see a lot more stars. Even though we can't use most of it yet because there isn't enough data, even just these like 2 places which are densely populated is a lot bigger combined than what Kepler can see. So it's a very cool telescope. And I'm specifically interested in what we call low metallicity or metal poor stars, because those stars are usually older. We know because of their composition that they were formed early in the universe's lifespan. That's what it tried to say. Yeah, and so I think that's it. But metal poor stars are a pain in the butt. They're really hard to observe because there aren't that many of them. So that's what's helpful about TESS is we can see more stars, so we can see a decent amount of metal poor stars rather than just like 10 or something when we're using Kepler. So I'm looking at about 500 metal poor stars, which is a lot relatively. So these are sort of the results from my project. These are the masses of the stars. I talked about earlier how stars burn hydrogen and then helium. So these are the 2 different stages of stars. These are pre-helium burning and post-helium burning. So this is before that helium flash and after that helium flash, but that's not super important. So the first thing I noticed is most of the stars are in these lined regions, which is about where they should be. So that's good. So the majority of stars are the masses that we think they are, about 1 solar mass or the size of the sun. But there's a lot of lower mass ones, especially in the post-helium burning. And this means that we think that stars actually lose mass as they go from one stage to another. So that was pretty cool to see, because that's not like confirmed yet, it's just a theory. So yeah, we actually notice that stars are losing mass from that transition. And then there's a lot of high mass stars, which translates to low ages, which they shouldn't be. These should all be old stars. So that was a little bit weird, but we thought that they might be mergers between stars. So if 2 really old stars have merged, then their asteroseismology would look like a young star, but the stars would actually be a lot older. Yeah. Okay, so these are the ages of the stars. Oh, do you have a question? Yeah. Yeah. Yes, that's correct. Oh, sorry about that. Okay, so she was saying that I talked about bigger stars have less mass, or like these stars are giant stars, but they have less mass than the massive stars which are smaller. Am I saying that right? Oh, right, right, right. Yes. Okay. Sorry. That's a great question. So, okay. As the star goes from this stage to this stage, it's losing mass, but it's increasing in energy. So it's getting bigger because the extra energy is pushing those outer layers out. So that happens essentially because of that extra energy. It pushes the outer layers out more, but it doesn't add any mass. So the star stays the same mass its entire life until it dies. But it changes size based on how much energy it's burning and how well it balances out the gravity of the star. So those two are sort of constantly at war. When they're balanced, it's good, but as the star starts to die, it loses that equilibrium. And so sometimes the gravity is winning, sometimes the radiative energy is winning. So it sort of pulsates. That's where we get these pulsations from. Does that make more sense? Okay. Thanks for the question. I'm sorry about that. Okay, so these are the ages. So this answers your question. Finally, so we think that the age of the universe is about 13 billion years. Some of our stars are older than that. We're just gonna ignore that. So we have a lot of young stars, which, like I said, we shouldn't have. But again, this might be mergers sort of disguising themselves as young stars when they're actually older. So we think that that explains this giant spike here, which really shouldn't be here. That was worrying at first. But a lot of the stars are about where we think they should be, which is about 8 to 12 giga years, which is billions of years, by the way. And yeah, that's about it. So we see two big spikes. We see more old post-helium burning stars. Again, that's because the lower masses correlate to higher ages. So, yeah. Okay. So conclusions from all of that is basically now we have the masses and ages of the Milky Way's oldest stars. So that can tell us about the history of the Milky Way. And we can also successfully use asteroseismology on metal poor stars from TESS. Metal poor stars are especially difficult to use asteroseismology on, so we weren't even sure if we could do that, but we can. There is enough data from TESS to do that. And next, I hope to create an astroseismic age map of metal poor stars in the Milky Way using data from all of the astroseismology telescopes. So that just means getting the ages of all of the stars in the Milky Way and then making a little plot of them like color-coded by age or something, so we can see when different sections of the Milky Way were born. That's my goal. Okay, so this is what we talked about. We talked about the scales of giant stars, stellar classification, and the HR diagram, the stages of stellar evolution, and then astroseismology and its applications. So thank you for sitting through all that. Oh, I just wanted to bring this up real quick in case you have children or grandchildren in public school. So we bring this mobile planetarium to public schools and give little planetarium shows, like Jane explained so kindly. Yeah, and we'll go to any school as long as it's within an hour-ish of Gainesville and bring the planetarium. So please email me or let me know if you're interested in that. And okay, that's all I have. Thank you.
Well, Corinne. Oh, Corinne, that was stellar. And it really clarified some things for me. So thank you very much.
Okay. we have
Now
a
for the questions.
question right here.
Corinne, could you go back to this metal poor star that you're talking about? Now, is this related only to its age, or is there something unique in the formation of that star? or the evolution of that star that has made it metal poor?
That's a great question. And the answer to both parts of that is yes. um, so these stars formed early in the universe, and we think that there were less um, of the higher mass elements because supernovae create those bigger elements, stuff like the stuff that starts with U at the end of the periodic table and that kind of thing. Yeah, and so all of that creates more stuff which sort of drowns out the metals. Or sorry, it overpopulates the metal part of the star. And so we think that before there were a bunch of supernova, then stars must have been metal poor because all that there was hydrogen and helium, basically. Exactly. Yes. So nothing about the metal like contributes to its evolution, but it just indicates that the stars must have formed when there were less metals, if that makes sense. Thank you.
There's someone back there.
So I would like to go back to your discussion of black holes.
Yeah.
Which I find really interesting. And in particular, you talked about the magnetic pull being so great that it actually bends time, and I think you said light.
Yes.
Now, you're talking about something that defies the fundamental precepts of physics.
Yes.
And I have absolutely I cannot understand how that could occur.
Yeah. So that is a great question because it's extremely weird. One time I had a sixth grader ask me that. I was so surprised they could think of something that smart because that's a great question. But yes, black holes bend light, which shouldn't happen because light does not have mass. And so, how is the mass of the black hole affecting it? Well, that's because the black hole does not only bend time, but it bends space. So, it makes it look as if the light is traveling in this weird path when it's actually just coming straight towards us. Um, the best example I've seen of it is if you imagine like a big rubber sheet and you drop a ball onto it, and then you try to roll another ball across the sheet, it'll sort of fall into that ball that's holding down the center of the rubber sheet um, instead of just going straight like it should. Um, so it's hard to explain in words, but that's sort of the best example I have. I should have put a picture of it. But does that explain it a little bit better? Or okay, thank you.
If I understand it correctly, in that HR diagram, our sun is pretty ordinary star, sort of in the middle of things. Uh, my and the seismic waves that you can see in stars, what do we know about our sun compared to other stars? Sort of the questions are those seismic waves related to sunspot activity? Is that what we see? And if if the seismic waves are used to calculate I don't know, the probability of planets, how many stars are similar to our star and that might have planets like our solar system?
Okay, that's all a really great question, by the way. So it's actually a problem that the sun is the only star that we can observe the seismology of very, very well because we can stare at it for years and years and years, and it doesn't cost a lot of money like the rest of the stars do. So we know the most about the seismology within the sun, and actually all of our other equations are based off of what the sun does. And metal poor stars are very, very old and different from the sun. So that sort of creates a problem for me when I study them. I have to like factor in a bunch of extra stuff because they are so different from the sun. But we do know a lot about the sun. It's called helioseismology. And I think, did you have a second part to your question? Okay, he asked, are there a lot of stars similar to our sun? And the answer is yes, but I'm specifically just looking at the giants because that's all that we can see because they're very, very bright and they're towards the end of their life. So we sort of know that they're dying and they should be really old because they're at the end of their life, if that makes sense. Yeah. Thank you.
Okay, Larry Lowenthal. We've seen evidence going back a century, over a century, that stars can bend light. And more recently, the black holes can bend light. What evidence is there that black holes bend time?
Oh, that's a great question. There's no evidence because we can't get up close and study them. But we do know that light bends around black holes, and light and time are directly related. You can't have one without the other. So if it does bend light, like we saw, we know it must bend time. But also, it started with Einstein's equations. Before we even knew that black holes existed, he came up with a theory that nothing can travel faster than the speed of light. And so he sort of altered Newton's equations to fit that theory. And we know that that must be true around black holes because that is the fastest that anything can go because the gravity is pulling it so hard. So we know that it must sort of almost break the laws of physics, and it must use Einstein's equations. And I think that answers your question, but I'm not sure.
Not really, no.
Okay.
It's okay.
Another black hole question. Does anything maybe unconnected to gravity ever come out of a black hole?
That's a great question. No, not really. Some people think that there are white holes, which would expel everything within it, but that hasn't been proven, and I personally don't think they're real. But no, nothing can come out of a black hole. That is like the one thing that we know it can't do. But yeah, we do know that they radiate away over time. So there could be some radiation coming out of the black hole, but it would not be very much. They radiate over trillions and trillions of years, and the Earth or the universe is only a few billion years old. So it's negligible, but maybe it does a little bit. Yeah.
I should have started by saying thank you. This was so much fun and really fascinating.
Oh, thank you.
But leaving black holes for a moment, going back to the high mass stars that develop into, is it the neutron dense stars? So the very powerful magnets, one would assume that they would then pull in or collect metals from, I don't know, maybe nebula, nearby nebula. And if so, how does that change the evolution of that star, the neutron star? Thank you, yes.
That's a really good question. I've never thought about that, so I don't know the specific answer. I do know that stars, this picture sort of shows it, they accrete things. So if they do attract metal, it isn't directly to the star. It sort of like approaches and then just misses it and goes woo, and then sort of ends up in this orbit around the star and becomes this nice, pretty disk that we see and that we see around black holes too. So that's what happens when it gets too close to a nebula and magnetically attracts it. Well, yeah, and I'm not sure how the magnetism ties into it, but I know that this is how like really, really strong gravity works. So I assume magnetism is similar, but I hadn't thought about it like that. That's a great question. Yeah.
Question. You've been talking about bending space and time. Do we know what, if we were there near the event horizon, what does it feel like when time bends?
That's a great question. I forgot to include that. I meant to. So we have a theory called spaghettification, which I love the name of. But it basically says that as you get close to a black hole, the gravity gets so weird that it pulls in your legs a lot more than like your head. So it would basically stretch you out over time. And then because it's a black hole and you're traveling at the speed of light, because you must be traveling at the speed of light when you're at the event horizon, that's just part of it, time would stop because when you're at the speed of light, time stops because it's all related, like speed and time and space. It's a little weird, but yes. So you would basically being stretched out forever. It would not be pleasant. I don't recommend it, but
In one of the Cosmos Nova series, there's actually a video or a animation of that stretching thing that goes on. That, yes, it doesn't look comfortable. No.
yeah.
Well, do we have one more question up front? All right.
In terms of, Neil Holland said, in terms of the satellites, the telescopes, how many are there, and are there new ones that are coming online that would enhance your ability to analyze stars?
That's a really great question, and a very exciting one because yes, there are new telescopes coming out. For asteroseismology specifically, we need telescopes that stare at stars for long periods of time, and we have two telescopes like that, which are Kepler and TESS. Kepler's dead, but TESS is still running. So right now we only have one asteroseismology telescope. There are a lot of other ones, but they look at different regions of the electromagnetic spectrum. So I want the visible light, but there are a lot of telescopes that look at X-ray, gamma ray, radio, all of that. But there is new asteroseismology telescopes coming out. I'm working on a proposal for one, which would be really cool if it got accepted. But we know that there is one coming, I think within the next year, and it's called the Roman telescope. And that will specifically look at stars at the galactic center. So very, very close to that black hole at the center of our galaxy. And so we can see what stars at the center of the galaxy look like, because we don't know if stars started forming at the center of the galaxy or outside at the edge of the galaxy. So looking at those stars in the middle of the galaxy will really help us understand sort of how the galaxy evolved over time. So I'm really excited for the Roman telescope, but yes, that should come out 2026, 2027. Yeah.
So Chrissy's going to close the presentation and check to see if there are any questions on Zoom. So you can go ahead. Okay.
Any questions online?
Okay. We are good, and we thank you for being here and for being at our whole course. Totally enjoyed having you all here.
And there will be a course on planets that's, I think it's next fall or fall. I think it's when it is. There'll be a course on planets, which Phyllis Saarinen is facilitating. So it'll be another good astronomy class.
Thank you so much.
Thank you very much.
Thank you.